Good afternoon, everyone. It's my pleasure to have this great opportunity today to share with you some of our recent and ongoing work on quantifying methane emissions from China based on satellite and surface observations. Before I move on, I would like to acknowledge my collaborators from Zhejiang University of Technology, China Meteorological Administration, and the University of Leicester, and many others. I would like also to acknowledge my funding sources. I also like to thank my group members. It has been a wonderful journey working with them in the last 2 years since I started my position at Westlake University. Everybody here already knows methane is a very powerful greenhouse gases whose concentration has been increasing since industrialization, together with other greenhouse gases, CO2 and nitrous oxide. This increase has been very rapid in the last few years. So it is not only necessary, but also urgent to contain this growth of methane concentrations in order for us to meet the below 1.5 and 2 degrees Celsius climate goal under the Paris Agreement. With some variations among different estimates, but by varied estimates, China is the country with the largest anthropogenic methane emissions. The emission from China is roughly estimated to be 55 teragram per year, which is about 10% of the world total. And compared to the sector distribution of the global methane emissions, China's methane emission features with two large contributions from two major sectors, rice cultivation and coal mining. These two sectors combined account for more than 50%, more than half of the China's methane emissions. In comparison, their fractions are only about 10% worldwide. And also, these two sectors are not only major methane sources; they are also very important, closely linked with the food and the energy supply to this 1.4 billion people and the second largest economy of the world. In addition, livestock and the waste management, their fractions are similar between China and the world, while the natural contribution from natural sources are comparatively small in China. Frankly, the importance of controlling methane emissions have not been fully recognized by the Chinese government and the industry until very recently. In 2020, the Chinese government submitted its national determined contributions to the UN under Paris Agreement, declaring its intention to reach carbon neutrality before 2060. And in 2021, last year, controlling non-CO2 greenhouse gases was for the first time mentioned by the central government in its 5-year plan. And last year, during the Glasgow Climate Summit, the US and China declared a joint agreement on enhancing climate actions in the 2020s. And in that agreement, there's a section dedicated to controlling methane emissions, in which China declares its intention to develop an action plan on methane aiming for significant reductions in 2020. Therefore, the stock taking or the knowledge about where and how large the methane emissions are becomes very important before the country makes any good and implementable action plans. And that's what we are aiming for. Our current knowledge about China's methane emissions are mainly based on so-called bottom-up inventories. A common challenge to these bottom-up inventories is that the emission factors are usually quite uncertain because of the lack of localized emission factors that can reflect the local practices. Also, there's a lack of availability of local activity data at a subnational level. Therefore, this kind of bottom-up inventory usually has some difficulties in capturing changes within like decades. The right figure shows a recent bottom-up modeling work by Liu et al. Published in ERL. In addition to their central estimate, they also estimate the uncertainty of their emission estimation. The uncertainty is mainly accounted for of the uncertainties in emission factors and activity data. And the range you can see is quite large. The 95% confidence interval is as large as 25 teragram per year. Alternatively, we can use atmospheric observations to constrain or to estimate China's methane emissions, which is the approach that we are taking in this study that I'm going to present today. However, there's also several challenges with this approach. For example, the synthesis paper by the Global Methane Project point out that there's a general lack of available long-term in situ observations in many of the important source regions, including China. So the current studies tend to use the satellite observations to constrain methane emissions in China. For example, showing on the right is the work done by Miller et al. Published in 2019. However, there's also challenges associated with the satellite data. For example, there's a lack of validation site for satellite data over China and in general over East Asia. In addition, these observation-based inversions usually use the cost resolution model and inversion. That means they have limited capability to resolve methane emissions at subnational levels. Also, the inference from these inversions are also affected by the inaccurate prior sectorial emission distributions, which I will elaborate in a few slides. We can also notice that the two studies we just mentioned, on the left, the bottom-up modeling by Liu et al., and on the right, the satellite-based inversion by Miller et al., infer very different methane emission trend from China after 2010. The bottom-up studies infers a relatively flat emission trend after 2010. That was mainly driven by the fact that the coal mining, the coal production from China has leveled off in has peaked in 2012 and even started to decline after that. However, based on the satellite data, the inversion conducted by the work showing on the right shows that there's still quite significant increasing trend of methane emissions from China. The trend is actually similar to the period before 2010, where the co-production increased significantly rapidly. But a recent study by Shen et al. Point out that the result from the atmospheric observation-based inversions can be affected by the uncertainties in sectorial distributions. This uncertainty affects not only the influence of the total methane fluxes, it also affects sector attributions. From this figure, we can see this figure shows a different bottom-up emission inventories for coal minings in China, and we can see they have a very different magnitude, and they also have very different distributions. And based on these very different emission inventories, Shen et al. Using the same GOSAT satellite data as the Miller et al. Derived a much smaller emission trend, which is only about 0.4 teragram per year squared, as compared to the 1.1 teragram per year squared derived by Miller et al. Here we will also take the inversion approach, but in which we update the prior emission inventory, statistically optimize the prior emission inventory by comparing the atmospheric observations with simulated methane concentrations, which is generated from a forward model, which is again driven by prior emission inventories. And the optimized emissions is called a posterior estimate, which is the outcome of this inversion analysis. And in this work, we are trying to make several efforts, trying to address the challenges, several challenges that we mentioned a few slides back. The first effort is in this work, we will try to use GeoScam model simulation as a forward model. The model is in a relatively high spatial resolution, 0.5, roughly 0.5 degree. So this will enable us to test if this satellite as well as surface observations can help us resolve methane emissions at a subnational level. In addition, we also, because this is a regional simulation and a regional immersion, we also use it requires boundary condition, and we use the boundary condition generated from a global immersion. So we make sure that our regional immersion and the regional simulations are consistent with the global observations. And the second effort that we make is trying to not only use GOSAT satellite observations from between 2010 and 2017, we also include surface observations in our immersion. In particular, we include new data from a surface network of 7 sites operated by China Meteorological Administration. The figure on the right shows the locations of these surface sites. We can see they are distributed across China, and they are located in several of the major source regions within China. by jointly using satellite and surface observations, we are trying to leverage their respective advantages, meaning the better spatial coverage from the satellite observations, and the better precision and better sensitivity to surface emissions from the surface observations. A work by my former colleague Lu Xiao has shown in his global methane inversion analysis that satellite and surface observations actually provides complementary information to constrain methane emissions at a global scale, which can be shown in the left column, that the DOF, which is the independent pieces of information obtained from the inversion, increases when we combine satellite and the surface observations. So we will take a similar approach here, but apply it to China. And the third effort we made is to try to address these uncertainties arising from the different prior emission inventories. So here we try to use a set of 4 different anthropogenic methane emission inventories in China. So to form a inversion ensemble, so we can characterize the uncertainties using this inversion ensemble. And this slide shows our mean results averaged from this inversion ensemble. On the left, it shows the distribution of mean methane emissions. And on the right, it shows the methane emission trend inferred from our inversion between 2010 and 2017. Aggregating nationally, we obtain our best estimate of China's methane emissions to be 55 teragram per year, with the linear emission trend about 0.7 teragram per year squared. We also examine the observational constraint provided by the observations. This plot shows what so-called average internal sensitivities, which is a metric we can obtain from the inversion calculation. The 0 values means the observation has no constraint on emissions, and the higher value means it has more constraints. Comparing the left figure using the both satellite and surface observations, and the right figure using only satellite observations, we can see the average internal sensitivities is increased in several regions, especially over Northeast and East China, when we use additional surface observations. And this can be better seen when we aggregate by region. The inclusion of surface observations can increase the number of independent pieces of information constrained by the inversion in all the regions. And it is especially, the increase is especially large over Northeast and East China. For example, on the right figure, it shows the DOFs, which is the independent piece of information, is more than doubled for emission trend of Northeast and East China. The reason for that is that the coverage of satellite observations are relatively sparse over those regions because of frequent snow and cloudy conditions. So this shows that the value of including surface observations. This slide shows our inversion inverse methane fluxes aggregated nationally and by region. In addition to these central values that we care about, what we can also see is that the error bar, which represents the range from our inversion ensemble using different emission inventories. This range has been considerably reduced from prior to posterior, which is consistent with the previous slides that the observations or the inversions has quite a strong constraints at the regional level, both for the average emissions and also for the emission trend. Also, it's to a less extent in the case of emission trend. We then further attribute our posterior emission fluxes to different sectors based on prior sectorial distributions to generate the posterior sectorial emissions. But remember, we use the different sets, a set of 4 different prior emission inventories. Therefore, we will also get an ensemble of 4 different posterior sectorial emissions, and that will help us to have some understanding of the uncertainties. And in the case of this study, we are actually more interested in attributing the posterior emission trends to different sectors. So we can have some, we can look for some insight of what drives the changes in methane emissions over China. And several quite interesting patterns emerge from this sector attribution practices. First, we find a very interestingly divergent trends of methane emissions over China, spatially divergent. And on the right, it shows the result aggregated by the country and by region. And we can see, although our inversion ensemble members does not agree even on the sign of the trend for the whole country, this seems to have some agreement on the regional trend. And when we combine this inferred trends with more bottom-up on-the-ground information, these spatially divergent coal mining trends started to make some sense. On the left, it shows that over the whole country, the coal production has peaked in 2012, and after that, it starts to decline. However, the trends are very different, very region-dependent for different regions. For example, indeed, the coal production has been decreasing quite rapidly in southwest and northeast China. That's where most small coal mines are. And however, the coal production has not been decreasing. It's actually even increasing in the major coal producing regions in North China, including the Shanxi province and its neighboring province, Shanxi. I think this is consistent with the coal energy policy in China, that they take priorities to close off small coal mines, which are concentrated in southwest and northeast China, and consolidating to large coal mines, which are often found in major coal producing regions like Shanxi and Shanxi. And indeed, from our result, we can see a significant decrease in methane emissions in southwest China. This is consistent with close of small coal mines over there. And we can see increases in North China region, and this is consistent with increasing production over that region. Although I think that this close small coal mines consolidating to large coal mine policy is not out of the consideration for methane emissions, but very interestingly, we find that they are actually cost effective for controlling methane emissions. So on the left, we normalize the inferred coal methane emission with the coal production for every province, and we can see that for the southwest regions, the small coal mine regions are associated with high emission factors, meaning they emit more methane for every unit weight of coal produced. And also, another interesting thing is when we zoom into the North China, where where there's the major coal mining regions, we can also see this divergent trends patterns. We can see there's a decrease in methane emissions in the sort of Henan province and the southeast Shanxi province, which is kind of puzzling me, because the county level statistics also tells me that this region, in this region, the coal mining activity or the coal productions has not been decreasing, and the coal production in this region is high as well, showing here in the left figure with this dashed line. And it turns out this region is actually quite special. It's called a Qingshui Basin, which is the largest coal bed methane production basin in China, responsible for about more than 60% of the coal bed methane production of the whole country. And the coal bed methane production also has been increasing during the years. This is a show on the right figure. So I think the decrease in methane emissions over this region that inferred detected by our inversion is probably associated with the produce gas first and then produce coal strategy that is adopted during the coal bed methane production. That means the methane gas which would have been emitted during the coal production now have been extracted and collected during the coal bed methane production. And I find that this, if this is indeed the case, and then I think the coal bed methane strategy should be promoted, and in terms of reducing the emission intensity, meaning the methane emissions per unit energy produced. In addition to coal, our inversion also find an interesting pattern related to another important sector, which is rice cultivation. We find an increase in methane emissions over these rice cultivation regions in South and East China, as well as Northeast China. And this is somewhat unexpected, because rice cultivation areas did not increase in East and Central China. This is shown in the right figure, that almost all the prior emission inventory predict a very small or even zero trend in rice cultivation emissions. In contrast, our inversion finds a relatively large trend over northeast, east, and central China. To explain this finding, we propose two hypotheses. The first one is perhaps the reason we find increased methane emissions over rice cultivation region is that we in our inversion or in all those prior emission inventories, we fail to account for the emissions from freshwater agriculture, which is overall spatially overlapping with rice paddies. The left figure shows data from a paper published in Nature Climate Change, which estimated the methane emissions from freshwater agriculture over the globe. And we can see that China is indeed the largest producers and consumers of freshwater fishes. And therefore, it has the largest methane emissions, nearly about 3.5 teragram per year, which is not negligible. However, the current emission inventory that has been widely used in analysis and in our inversions does not account for these contributions. So we collected some statistical data to see if by including freshwater agriculture, can we explain the emission trend that we inferred over these rice cultivation regions. The second hypothesis that we propose to try to explain this increase in trend over rice regions is there may be increasing straw incorporations into these rice paddies in the recent few years. Straw incorporation is a agricultural practice that is promoted by China's agricultural policy, apparently because by incorporating straw into the rice paddies or crop fields, it can serve to increase soil carbon and increase crop yield. And it is also a practice promoted by environmental policies in order to decrease straw burning in the crop fields for a better air quality. So we believe that it is likely that the straw incorporation have been increasing over the years. And it is widely or well documented that by applying straw residues into the rice paddies, the methane emissions will increase significantly. This is shown in the field experiment. For example, showing here is a recent study by Nan et al. Conducted in Zhejiang province, which is where I am. And we can see from their figure that by applying straw residuals to the field, the methane emissions is more than doubled compared to the control group. Although there's although there's not many public available data on straw incorporation practices over the whole country, we managed to find several data sources. Actually, two papers conducted in 2011 and 2016. And comparing their data, we do find increased fraction of straw incorporation in the major rice cultivation regions, namely the northeast, east, and the south. So with these two hypotheses, we conducted bottom-up modeling to see if they are important enough to explain the trend we are seeing from the inversion. And the figure shows our result. The green bar shows the emission trend attributed to rice from our inversion. And the purple bar shows the inversion, the bottom-up calculation we did for the agriculture. And we can see, except for the central China, it appears that the agriculture cannot explain the inferred trend. And the pink and the orange bar shows the bottom-up calculation of rice emissions without considering the trend in straw incorporation and with the trend of straw incorporation. And we can see from the orange bar that by accounting for the trend in straw incorporation, it seems it can explain a significant fraction of the trend that we inferred from the inversion. So this bottom-up calculation, although admittedly it has very large uncertainties, and the two hypotheses we proposed probably are not the there's more other alternative hypotheses, but based on the information that we have, it seems that the increases in straw incorporation is an important factor that driving the increase of methane emissions over this region. This suggests that the agricultural practices matter for the methane emissions. It is important to consider the variations of these practices in the bottom-up modeling, and it's also important to consider the practices in order to form some action plans in the agriculture sector. So the take-home message from this China surface and satellite observation inversion is that China methane emissions and their trends can be readily constrained at a subnational level by a joint inversion using satellite and surface observations. And we find several interesting patterns of emission trend, and they are closely linked to the energy, agricultural, and environmental policies that has been implemented in China in recent years. And we recommend to account for practices in energy and in agricultural production in both bottom-up modeling and in formulating future action plans. And in the next a few slides, I will spend just a few slides to share with you an ongoing study led by my student Ruo Siliang, because it is still quite preliminary, but I want to share with you because it echoes with another challenges that I mentioned in the very beginning. That is, these satellite data are in general not very well validated and evaluated over China because of a lack of validation site. But here we will take a slightly different approach. We're trying to compare inversion results from using different satellite products. So in addition to the GOSAT satellite we used in the previous study, there's a new satellite called TROPOMI, which is launched in 2017. So in the recent few years, we have 2 different satellites observing methane column density over the globe. And these 2 satellites, provides retrieval products using different methods. For example, the TROPOMI provides so-called full physics retrieval, while the GOSAT also provides so-called CO2 proxy retrieval. So there's no easy guarantee that these retrievals are equivalent or are very close. So we are trying to make some effort to compare and see if they are consistent. So the first step we did is to use the chemical transport model, such as GeoChem, as an intercomparison platform to compare the concentration observed by TROPOMI and the GOSAT. By using the chemical transport model as an intercomparison platform, we can properly account for the fact that different satellite retrieval product has used different prior vertical profile, and their instrument have different vertical sensitivity. So it provides a more fair comparison between the different products. And we can see from the figure that it seems that TROPOMI methane product shows a higher overall higher concentration over eastern China, as well as over northwestern China and the neighboring country Kazakhstan. And we apply this different satellite retrieval product to our inversion system. And these figures shows the posterior emissions subtracted by the prior emission. So we can see that the 2 inversions using different satellite retrieval product does produce some consistent results over some regions. For example, the results are consistent over northeast China, central south China, and the Bangladesh area where there's a major wetland. But meanwhile, these 2 inversions are also quite different over important source regions. For example, in the over the eastern China, where the major emission also over the North India, which is another important methane emitting region. And the difference over eastern China seems to be explained by the difference in their methane column concentrations, as shown in the last figure. But over India, we actually see these 2 products compare relatively well. So we did some experiment, and we find that the difference is mainly due to the fact that TROPOMI satellite product has a much better coverage over this India region, and that results in different inversion results between TROPOMI and the GOSAT. And the next step we would like to do, but if this is still ongoing, is to use independent data to evaluate these 2 different posterior emission. And we plan to use this surface size that we used in our previous work. We also are looking into using the TCOM sites that are located within China. One is located in Beijing, and the other located in eastern China in Hefei, because the key concepts are measuring the total column, so it is more comparable or more proper to compare them directly with satellite observations. And over India, we don't have any access to any surface observations, but we do find some interesting data from a commercial aircraft database called Carabic. And over India, these airplanes are flying in the troposphere. So we are looking into the possibility that to use this data set to compare the different results that we inferred over India. So with this practice, we are trying to show that inversion and model simulations can be used as an inter-comparison platform for different types of observations, and even for different periods. So the take-home message of this second preliminary study is that if we really want to characterize the uncertainty of our inversion, another work we need to do is to have a systematic evaluation and validation of these satellite retrievals, and to evaluate their impact on the final emission inversion results. And our study shows that the TROPOMI and the GOSAT inversions are indeed consistent over some regions, but they are also inconsistent over some other regions, including very important regions like Eastern China and Northern India. So it is very necessary that we bring in more independent data to kind of determine which one is performed better. And if one of the satellite product is inferior than the other, we also want to ask why, and is there any way to improve? That's the work that we would like to do in the future. And this is all of my presentation. Thank you.